We've now gotten through a number of different problems in this course, and along the way, we have seen many problems where we put together many different solutions. So in some cases, we did 2 solutions or even 3 solutions in some cases. As we compared those different solutions, I made a very personal claim and I said, oh yeah, I think this solution is better than this one because it is easier to code, or it's easier to come up with, or it just looks better. However, there is another way of comparing all these different solutions or algorithms that we are writing that is much more concrete than what I was telling you. So in this section, we're going to start to investigate this much more concrete way of deciding what given solution is better than another. So this is where we are going to start to talk about something called runtime complexity. Runtime complexity is a term that we use to describe how performant an algorithm is. We use runtime complexity to compare different solutions to a given problem, or different algorithms for solving a given problem. In the context of an interview, so in the context of like you going and interviewing with someone, you are going to be asked very frequently in many different interviews, many times, you're going to be asked what the runtime complexity of a given solution is. So usually an interviewer will ask you a question, you will solve it on a computer or on a whiteboard, and then they will turn to you and say, okay, what is the runtime complexity of this solution you just did? So the real goal with runtime complexity for you and me, like in this course right now, our goal is to make sure that you have the ability to identify a given runtime complexity. That's our goal. That's what we're trying to learn here in this video and the next few. So just keep that in mind. Now, when we talk about runtime complexity, we're really asking a very discrete question here. We are saying, how much more processing power do we need to run a given algorithm or a given solution if we increase the number of inputs into our algorithm? So let's look at some examples of this right here and try to answer this question. Let's look at some examples of some problems that we have worked on and try to figure out what their runtime complexity might be. So the first problem we are going to look at is the string reverse problem we worked on. And let's pull up the code from that very quickly. So back in my code editor, I'll pull up reverse string. Here it is right here. And I want specifically to look at the iterative solution that we put together that used a for loop. So for this problem right here, we said that we would have some input string. And then to execute our algorithm or our solution here, we iterated through each character of that string exactly one time. So it would be fair to say that as we started to add one additional character to the input to our algorithm, or like the actual input string that we threw in there, we had to do one additional step of work. So for each one character, one additional step. So that meant that we had a very linear runtime. We would refer to that as a linear runtime because there is a direct one-to-one relationship between the number of input elements that we got into our algorithm and the amount of work that we had to use to process it. Many of the problems that we've been working on so far have been linear runtime, but we've also had a good example of another problem, actually several other problems that we've worked on that had a slightly different runtime, one that was not linear. So let's look at an example of one of those. So here's the steps algorithm that we worked on. And let's pull up the code from that one as well really quickly. I comment that back out, and I'll pull up my steps code. Here it is right here, and I want, again, specifically to look at the solution with for loops. So here's the for loop right here. So with the for loop, we took some input n right here, and then based on the input n, we had 2 nested for loops right here. So one nested inside of the other. That meant that as we started to increase the value n into our algorithm, we had to do significantly more things each time n was increased by 1. So when n was equal to 2, we essentially had to do 4 things. We had to produce 1, 2, 3, 4 characters. When n was equal to 3, we then had to do 9 things. And when n was equal to 4, we had to do 16 things. So in this case, there's clearly not a one-to-one relationship between the input to our algorithm and the number of things we had to do, or the amount of processing power that was required. In this case, the number of things that we had to do was n squared, or we had to do essentially n times n things to execute our algorithm. So when you have to do n times n things, we would refer to this as an n squared runtime complexity, or a quadratic runtime. So we get these kind of different terminology for identifying our runtime. We get both this kind of equation looking thing right here, which is the n squared, and we also have this kind of nomenclature or a kind of a verbal form. And we would identify this as quadratic in this case. So let's take a break right here. We're going to continue in the next section, and we're going to look at several other very common runtimes, and we'll also start to talk about how we can identify the runtime of a given algorithm. So quick break, and I'll see you in a minute.